starting recording. So anything anyone says will be recorded, but the chat will not. And this will show up on YouTube. It's been taking about 35, 45 an hour for these things to show up on Blackboard. At that point, I can download them to my laptop and then upload them to YouTube. And that process takes about half an hour. It downloads really fast, but it uploads pretty slow. So there's that. So in any case, I expect these videos to be available for you by about 2 p.m. on YouTube at the playlist that I sent you. And it's really easy, youtube.com/ all one word, Professor Jesse N / playlists. And you'll see the playlist for our course in there. And you click and you see the videos. Okay, there we go. So the first thing to know about using laws of sines and cosines is if you have an opposing pair, you're going to use the law of sines. If you don't have an opposing pair, you're going to have the law of cosines. And when I use the standard grid, the side and angle that are opposing each other show up with the same letter. Capital A is for vertex A, is for angle A. Little lowercase a is the side that's opposite angle A. The side that's opposite angle B is little b. The side that's opposite angle C is little c. And again, these aren't right triangles now. Though all the things I say that would work if it's one of these is a right angle too, but there's the idea. For any particular side, there's going to be one, for any particular angle, there's going to be one side that's opposite, two sides that are adjacent. The side that's opposite has the same name. The sides that are adjacent have different names. Okay? So opposite is across, adjacent is anything that's not across. Okay, now here are the 4 different types of triangles we're going to solve using law of sines and law of cosines. Now, on the ends, we either have all 3 sides and no angles. The grid would look like the ones that I showed you as examples, where we have nothing but lengths on sides. And if you have no angles at all, then you're going to use, they can't have an opposing pair, and you use the law of cosines. If you have 2 angles on the other far side, you are absolutely going to use the law of sines. Okay? And I want to point out that special case, the one I used twice in the examples, where you had 2 angles, gives you a 3rd angle. Anytime you have 2 angles, you have the 3rd angle, and you're going to have an opposing pair because we always have to have a side. You can't solve a triangle without one side length to give it scale. Anything else, you're just going to have a whole infinite number of similar triangles that you're not going to know which one of those similar triangles is the triangle that you're looking at. You need one length to give you the scale. And you need 3 pieces of information to solve the triangle. Solving the triangle means knowing what all the angles are and knowing what all the side lengths are. Okay? So you want to have 6 numbers associated with the triangle to have it solved. And to solve it, you need 3, and one of those 3 has to be a side. If you have no angles, it's the law of cosines. If you only have one side, then it's law of sines. And that somehow got deleted from this because I told you weird things happen on me here. Okay? Let me fix that. This should say law of sines. There we go. Yeah. And now that leaves the middle cases that we have to pay attention to. If you have 2 sides, it could be law of sines or law of cosines. And that's the tough one to figure out, but it's not that tough, right? If you have an opposing pair, it'll be law of sines. And if you don't have opposing pair, it'll be law of cosines. But this one case, we're using law of sines, when you only have one angle, that's the one. This is called the ambiguous case. Okay? This one right here is called the ambiguous case. And it's ambiguous because in this case, it's possible to have two triangles that solve it. It's possible in this case to get two triangles. It's called the ambiguous case. And the way to remember that it's the ambiguous case, every textbook everywhere will say this happens with side-side angle. You got two sides and one angle, and the angle is not opposing. When I draw these, I start with the angle, and I don't know which the other side is. On all these diagrams, I've used a different color to signify the unknown. And this golden brown here, this is my unknown side. I start off, I know this angle, and I know the side, one of the sides is adjacent, but not the other. And I know how long the side opposite is. So I see an angle, and then the side adjacent, and then the side opposite, but I don't know the angle between the adjacent side and the opposite side. I don't know this angle. And that's going to cause some issues because this other side, it's possible for this thing to swing twice. And give me two answers. And so this is called the ambiguous case, and I'm going to give you a way of figuring that out. Now, the way to remember that's the ambiguous case, every textbook everywhere calls this SSA, all right? The construction to figure out that it's ambiguous starts by looking at the angle, okay? By construction, you actually, to see that it's ambiguous, you start out by looking at the angle. And then look at the two sides that are next to it. For some reason or other that I just can't figure out, even though it's most natural to think of it for ambiguous case as angle, side, side, for some reason that never shows up in textbooks. I have no idea why. So that's the case that you have to watch out for. All right? I don't know why they reversed that, but there it is. Okay? So again, if you have three sides, law of cosines. Two sides, law of cosines or law of sines, depending upon whether you have an opposing pair. And if you have an opposing pair, you're in the ambiguous case, the angle side case. And if you only have one side, then you're going to be looking at law of sines definitely. Okay? You'll be either immediately given, if you have one side and two angles, you have three angles. Okay. And that's how that works. Okay, now let's move over here and again erase all this extra stuff that I worked with. With my other classes and eliminate it because I want to write that as I'm going along and show you where that came from. I actually don't even want to let you to see that what I'm doing here. I don't want you to see this either. Okay. And there, we're good, okay? So the flow chart again. is if you have an opposing pair, you're going to look at law of sines. Otherwise, you're going to look at law of cosines. And the first thing, because it's easiest, is I want to show you the law of cosines. All right? Here, up at the top, I've just put it in for you. Okay? Here you go. Relative to side C, okay, if you want to solve for a missing side, this right here assumes that you have sides A and B and the angle that's between them. Okay? So this is the side angle side case, the SAS case. Okay? Now, I'm going to show you how you can see what's going on here. Let me erase this and ask you guys, what does that formula look like to you? Who knows what that formula is? What's that formula now when I do the erasure? What's that called? Yes, 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 yes. Thank you, Joshua and Anthony and Patricia. Yes, that's the Pythagorean theorem. The law of cosines, the Pythagorean theorem works for just for right angles, for right triangles. The law of cosines generalizes, it extends the Pythagorean theorem when you're not looking at right triangles. Now, the law of the Pythagorean theorem assumes that you're looking at C here as the hypotenuse. It assumes this is the hypotenuse, right? And the angle across from the hypotenuse is a right angle. Guys, what's the cosine of 90 degrees? What's the cosine of 90 degrees? Anybody? People know. What is the cosine of 90 degrees? Use your cofunction identity. The cosine of 90 degrees is the sine of 0 degrees. What's the sine of 0 degrees? No. No, not Josh. Not that Joshua. Yeah. The cosine of 90, remember? And I'll write that here too, right? Remember that cosine of 90 by the is the sine of the complementary angle, and that's your benchmark, sine of 0 is 0. Water. There you go. And yeah, so in this case, if this was a right angle, 90 degrees, its cosine is 0, and what happens? We're back to the Pythagorean theorem. So, other things you should notice, because cosine is an x thing, because cosine is an x thing, the angles that come at the arc cosine be running from 0 to 180. And notice right there, if the cosine was positive, cosine is positive, you're looking at an acute triangle. An acute, and if the cosine is negative, if the x value is negative, then you're looking at an obtuse triangle. Okay? That's just basic stuff. All right. So the cosines comes in two forms, and the one form is equivalent to the other one. The only difference between the two, this is the standard one that people use to find the missing side. If you see the cosine of C, then you get, well, bring it over to the other side and bring the C squared over, so C squared becomes negative, this term becomes positive, and divide by the 2AB. Yeah, there you are. And I use this form, I could actually use C equals the arc cosine of this thing, but I want you to see it, okay? You'll remember this because the cosine of the angle is the other two positive squares minus its own. Minus its opposing, and divided by twice the other two. Okay? And we'll show you symmetries on this as well. Now I'm going to prove this thing. for you guys because it's a fun exercise. Let's assume that we have a triangle ABC. And just to make the picture works, I let B be an obtuse triangle, but this would work just as well if it wasn't. All I know about this is that the distance from A to B is the length C. Okay? Now, what I'm going to do to make this happen is I'm going to start off here by insisting A has to be a central angle, which means it starts off at the origin. Okay? Now, if I'm starting off at the origin and moving a distance C away from that, the coordinate of B will be C. You write this carefully. C, 0. Okay? And now, for an angle B, for an angle or a side B here, an angle A, we know if this was a unit circle, if this was a unit circle, it was 1. Coordinates of C here will be cosine A, sine A. Yes? But because the length is B, not 1, the coordinates can be written as B times it just stood up. Multiplies that cosine A sine A times B, which I can then bring in to the coordinates, giving me coordinates for C of B cosine A and B sine A, just like that. Okay? And now the right triangle involved. If I drop an altitude from C down to the line, the positive axis line that I was using for the initial side for angle A, here is a triangle. Everybody sees that right triangle, right? Yeah. Okay, so now I am going to find the lengths. Okay, here is going to be a delta x. That's the change in the x values. Here is going to be a change in the y values. And I know the change in the x values squared. The change in the y value squared is going to be the hypotenuse A squared. Okay? And hopefully that's here. Right? All I got to do is figure out what that delta x and the delta y is. You know why delta, I hope. Okay? I hope you recognize why I call it delta. I'm calling it delta because that's the name of the Earth. That's the capital D in Greek. Okay? Now, let's calculate what the change in x is. For this, I need the coordinates of E. Okay, so what's the x coordinate of D? Anybody? They're actually, coordinates of D, the x coordinate of D is actually up there. The x coordinate of D is actually up there. The y coordinate of D is really easy. What's the y coordinate of D? Everybody be able to tell me what the coordinate of D is. This point here, D. What's the y coordinate? What's the coordinate of D? That's fake deal. Thank you, JD. 8 more to go. Mario, thank you, Mario and Elizabeth and Anthony and Miguel and Joshua. You're welcome. Yeah, and yeah, it's going to be the same y coordinate as is everywhere along the line. The y coordinate is just 0 here. The height right now, on this bottom line, the height is 0, right? Up here, the height is b sine A, but down here, the height is 0. Right now, I want the x and y coordinates of this point D. Okay? I got the y coordinate. It's the same y coordinate as the point A and point B. What about the x coordinate of that point? I want the x coordinate of this point. Yeah, I do want x and y, but I also want the x coordinate. The y coordinate is easy to see. It's just 0. What's the x coordinate of the point D? Anybody? You are so close, Daniel. You forgot the scale factor. If this was a unit circle, yeah, it would be cosine. But it's the scale factor. This is length b, not 1, so it's b cosine A. It's the same x coordinate as you have for the point C. This is b cosine A sine A. And so here, the length is b cosine A, and so that's the coordinates. And now I can figure out what delta x and delta y are. Not c cosine A, not c cosine A. What would that be? C cosine A would be the length of, C cosine A would be this length, right here. That'd be an altitude that way. And no, that's not what I'm looking for. Yeah, so B cosine A. Is you're thinking here, guys? You're thinking here is the origin, and you got a circle here that's starting from here, okay? And so this hypotenuse, this point right here is cosine A sine A times the scale factor B. Okay? And as soon as I got the whole point on that exercise was that making this into a right triangle is that these two x coordinates have to be the same. And these three y coordinates have to be the same. Okay, so now that we have the coordinates, we are ready to construct the proof of the law of cosines. Give myself just a little bit more real estate here. And again, it's going to be delta x, the change in x squared, plus the change in y squared. And I'm going to write more neatly. The change in x squared plus the change in y squared is a squared. And now we're ready to rock and roll. What is the change in x here? It's the difference in the two. It's going to be the difference in the two x coordinates. Okay? Because I'm squaring it, I don't care. I'm just going to write c minus b cosine A. And that's actually negative, but I don't care because I'm just going to square it. Okay? Now, what's the difference in the y coordinates here? What's the difference in the y coordinates from here to here? What's that difference? Yeah? The difference right there is going to be what? Here's a y coordinate, there's a y coordinate. What's the difference? What's the difference in y's, guy? Yeah, negative b sine A or b sine A. It doesn't make any difference because I'm going to square it, okay? So it's going to be plus b sine A squared, and that's going to be equal to a squared still. Okay, get rid of those. And now I'm just going to go ahead and multiply things out, see what happens. Okay, so there we got everything together and we're ready to just rock and roll. The square here is going to be c squared minus 2 bc cosine A plus b squared cosine squared A. And that's just from this term. plus b squared sine squared a, and that's from here. A little bit more real estate, is going to be equal to a squared. There we are. Okay. And so let's resolve these things with the parentheses, okay? So I'm seeing c squared minus 2bc cosine a plus b squared times cosine squared plus sine squared. Okay? And I'm betting that someone can tell me what this is. What is the value here? Yes, thank you, Daniel. Thank you, Anthony. Yes, that's just 1. And so now what we have is c squared minus 2bc cosine a plus b squared equals a squared. Turning this around, I get a squared equals b squared plus c squared minus 2bc cosine a. Cool? Cool? Yeah. And there you go, guys. Now, I know if I pop back up, somebody's going to say, but wait, you use c squared down here, and I proved a squared down here. Guys, each of these forms has symmetric forms. There was nothing special about my choice of A, B, or C on this. I could have made angle C, I could have made angle C my central angle in that proof. And if I'd done that, I would have gotten this C form of the law of cosines that I showed you up on top. I use this form not because it's the most natural form. I use this form because it looks most like the Pythagorean theorem. Okay? Now here's a cute thing that happens. To find the symmetric forms, you start off with one form. A squared equals b squared plus c squared minus 2bc cosine a. That's the one we just proved, okay? And there's a clever way for these to find the symmetric forms. Replace a with b, b with c, c with a, and you'll get the other forms. This works when you have 3 things that you want to swap around for symmetries. And that means I get the symmetric form b squared equals b goes to c goes to a, b goes to c, a, b. Okay? And now the form that we used to see. C goes to a goes to b, goes to a, b, cosine c. Those are the symmetric forms that we get. Okay? And we can do the same thing, just solve for the cosine in order to find the law of for the others, okay? Now, we got that kind of theory going on, and I've got what? I've just got another 15 minutes with you guys, right? Okay. So let's continue on. And now, I want to look at the law of sines. I want to look at the law of sines, and I'm going to provide that to you here. I think I'm just going to get theory for you guys today. I did a bunch of things to make this happen. Do I want to leave that? I'm going to leave a lot of that stuff in there. Okay, so let's go ahead and take a look at this. So here's the thing, guys. I got a triangle, ABC, okay? The law of sines comes from the fact, you get the law of sines coming from the fact, if I have two angles that are kind of sitting on the same side, okay, so I messed up. Okay, if I have two angles sitting on the side, that there's something that interesting that happens between them. Both of these angles have the same altitude. I can create from this just general triangle, I can create right triangles from this thing just by dropping an altitude between them. I generally call the altitude h, and the idea here is that the altitude, if I look from the left triangle, the left-right triangle, that altitude is going to be the same as the altitude looking at this right triangle. I could do this the same way, even if one of these angles was obtuse. We would still have an altitude, but it would happen outside the triangle. The altitude, and we'd have this right triangle showing up here, and this right triangle showing up here. And in either case, elevation is a y thing, is a sine thing. So this altitude is sine b scaled by its hypotenuse a sine b. Looking from the other side, it's sine a scaled up by its hypotenuse b. So a sine b is b sine a. And that's the basics. That's the basics. I can write symmetries on that. I can write symmetries on that the same way that we just did. Because there wasn't anything special about the way we set that up. A goes to B, B goes to C. B goes to C, C goes to A. Okay, and if I'm looking at these things, this is the form that you actually use it in. But when you're actually, this by the way is the altitude form for the sines, and this is the way you'll actually use it. But there's a really pretty presentation on it that's called the triple equality, the triple form, the triple equation form. Okay, and it comes from the fact, if you divide both of these by sine A sine B, if you divide these by sine A sine B, or equivalent divided by A and B, I get sine of A divided by A is sine of B divided by B. And if I do the same thing all the way around, you'll find that ratio works all the way through. And so this is the way of the form of the law of sines that you usually see. And this is the way it gets written, but it's not the way it gets used. What gets used is you identify altitudes. A sine B with B sine A. B sine C with C sine B. A sine C with C sine A. And I guess reassure you in a way, guys. That's a smoker's cough. I don't have COVID. I have actually been within 6 feet of 3 people in the last 3 weeks. And I hope you all are trying to stay safe too, for you and for your relatives. Okay. Now, there's going to be 2 cases where we have to work with things. We're either going to be looking with one side in which case we're going to have two angles that we don't know. We have two angles that we do know. We know the third angle. This is a pretty side. We have one side. If you have two sides, well, you know what that turns around to, right? Thank you, Daniel. This isn't a question of getting better. This is a question of decades of smoking. And that smoker's cough is going to be with me until I die. That's what bad decisions do. Okay? I'm not going to turn that into preaching at you guys. But, yeah, bad decisions, lack of adult supervision when I was young, I did a lot of things that I shouldn't have done. Some of which I'm very proud of, by the way. But there it is. Yeah. How many of you guys can say that you hitchhiked across the country 3 times by the time you were 14? Great stories. Some very scary stories in there too. Okay. Yeah, so that's the way we're going to be running these. When we're using the law of sines, we're going to move back and forth. But there's one case which is awful, 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 and I've got it all written up, damn it. Here's the problem, guys. The problem with the law of sines, damn, I got to erase all this. I had all that erased so you didn't see it before. Okay. It's all pretty. So I can mark it up. Now it's got all this other stuff. I need to eliminate somehow. I'll try to erase it the best I can. Okay. Oh, that's going to be impossible. Okay, I can get most of that. That's cool. Okay, so I'm setting this up to take a look at the ambiguous case, the angle side-side case. No way, I'm not going to be able to erase that without losing parts of those other sides. But this is the side that I want to lose if I want to do that, because I can redraw that. There we go. Oh, thank you. There we go. And now lose this, and lose this. There we go. Okay. And I'll leave that in there. Okay, so here you go, guys. The law of sines, you're going to see a lot of instruction on how to use the law of sines for the ambiguous case. Okay? And this is for the flow chart for the ambiguous case, guys. And this is not covered in your text. It's not a standard method, but as soon as you mention method of altitudes, for the method of altitudes, it becomes clear how you do it. Generally, instruction will always tell you just plug the numbers in and see if it gives you a domain error on your calculator, and that means that, well, you can't do that. I have a better way for you guys. I have a flow chart for you. We're going to compare the opposite to the adjacent on the ambiguous case. And we're going to figure out, using the opposite and adjacent and altitude, whether we're going to have one triangle or two triangles or no triangles as our solutions on this. Okay? And so, let me get this in here too. Is that it? That doesn't look like it. Yeah, that's it. Okay. All right, there we go. Yeah, okay. There we go. All right, so here's the thing. We're going to have this looking at opposites and adjacents, and obtuse, and then opposites and altitudes, and else. And this is a flow chart. One of these things is going to happen as we go along. Okay? And I will review this right here. We're just going to have a chance to just do the theory today. And we'll come back a little bit and come up with what's happening here. So, this is the flow chart. The flow chart always says you compare the opposite to the adjacent. If the opposite on your opposing pair is bigger than the adjacent that you're given, then you're going to just have one triangle, just one. The next thing you do is, and you're done, you just find that one triangle. The second thing is check to see if the angle is obtuse. Well, if it's obtuse and you failed the first test, so the opposite isn't greater than the adjacent, then there's no answers. Okay? Then you check to see if the opposite is greater than the altitude. And if that's the case, you get two triangles. Otherwise, you get no triangles at all. So basically, it's opposites greater than adjacent gives you one triangle. Opposite greater than altitude gives you two. Okay? That's how we're going to do it. I'm going to look at two cases here. One where my angle A is acute, and another one where my angle A is obtuse. Now, I want to point out again that I know this angle, but I don't know this side. I know this angle, I know this side, but I don't know the angle. And because I don't know that angle, this side is free to swing. Now, this angle is free to swing. A number of things could happen. It could be the case that it's too short. It could be the case that the length is just too short and it will never reach the bottom line. I don't know where this line, how long this line is, but I know what direction it's coming. And either it's possible it wasn't long enough to reach the line, in which case I don't get any triangles. So at the very least, it has to be greater than the altitude, because if it's not greater than the altitude, I just won't get there. It's also possible that I can get two. If it's longer than the altitude, I'm going to have this line swing and hit this line twice. If it's longer than the altitude, it will hit this line twice, giving me two triangles. And the nice thing about those two triangles, I didn't want that in orange. The nice thing about these two triangles is because of the symmetry, these two angles are going to be supplementary. Okay? Look at this angle, and then look at this angle. Okay? And what you notice is because of the perfect symmetry, look at the perfect symmetry, this angle is going to be equal to this angle, and this angle is going to add up with it to be 180. Why isn't that zooming? Because I got it locked, that's why. Okay, so the idea here is, if this swings, it gives me two places where it hits, then one of these, that angle, is going to be the same as the angle on the other side here, and the other side here. So what we're going to have here is that B1 and B2 have to add up to 180 degrees. They're supplementary. So if you get two triangles, the B1 and B2 are going to be supplementary, and use that. There's a little bit of a further complication if I'm looking at the angle being obtuse. If the angle is obtuse, I need the side that's opposite the angle that I've got to actually be bigger than the adjacent side. If it's not as big as the adjacent side, well, yeah, maybe it can hit this line, but it hits out. Here's inside the triangle. If it hits outside the triangle, that's not going to work. That angle's, I'm no longer inside the triangle. So it has to be bigger than this altitude. Bigger than this adjacent side. But then if it's bigger than this adjacent side, it'll hit here and it'll hit somewhere else outside the triangle. So if the angle is obtuse, the only choice is you can have one triangle if it's bigger than the adjacent side and 0 triangles otherwise. I push all those rules together and I find myself with this ambiguous case flowchart. If the opposite is greater than the adjacent, I get one triangle. Okay? The idea here is, in the other case here, if the opposite was greater than the adjacent, if this opposite was greater than this adjacent, when I swung, I'll get one, and the second side will be outside the triangle again. So if the opposite's greater than the adjacent, I'll get one triangle. If it's obtuse, I'm done. It's either one triangle or none. But then, if the opposite isn't greater than the adjacent, it's possible in the case where I was living with acute that I can come up with 2 places where it hits. For that to happen, the opposite has to be greater. The opposite has to be greater than the altitude. And in that case, I'll get 2 possible triangles that are characterized by first B, that as an obtuse angle, there's going to be an acute angle, and then there's going to be an obtuse angle on the other side. That's going to be the complement or the supplement of it. The ambiguity here on these problems is, on the law of sines, is that if you're looking for the other missing angle, you're not actually going to be solving for the missing angle. You're going to be solving for the sine of the different angle. I know I'm like 2 minutes late on this right here, but let me just go ahead and make this last point before we come back next time and clear this up and actually do our exercises. Okay, so here is a circle, okay? We are going to be solving for the sine of an angle. That's the whole idea on these, okay? Yeah. We have A sine B. We have one altitude. A sine B equals another altitude B sine A. Okay? And if we're looking for one of these, we're going to solve for a sine of one angle in terms of the other one. But the problem is this number right there, whatever that number is, it's going to be a y value because it's a sine, yeah? And that gives me 2 solutions. And those 2 solutions are going to be complements. One will be acute, and that's the one your calculator comes out. The other one is going to be obtuse, and it's going to be the supplement. And that's how that's going to work. And I believe I'm like 4 minutes out on what it is right there. When we come back, we'll start in on all of these examples from last time, okay? And we'll do a couple with the ambiguous case as well. That's very important. That will certainly show up on one of the exams. Thank you guys so much for your attention. I'm going to stop the recording now.